Thank you for being here for this further appointment of our science colloquia. Let me give my greetings for being here to our rector, Professor Priolo. Thanks a lot. And to our speaker, Professor Massimo Carpinelli. And Alessia, please introduce our speaker for today.
Thank you, Livio. Good afternoon, everybody. Of course, I'm also happy to see our rector here, and I welcome Professor Massimo Carpinelli here in our department and sezione INFN di Catania. Massimo Carpinelli is well known in Catania because he has worked together with us for many years. The list of appointment of Massimo is very long. I just remind everybody that Massimo was the president of the INFN Committee 5, which take care of all the applied physics, development of detectors, and so on. For many years, he contributed to high energy physics, so what we call Commissione 1, and later, he moved to very important appointment, being the rector of the University of Sassari. Nowadays, he's in charge of the EGO laboratory. So he moved to take care of a very important item in current understanding of physics, of astroparticle physics, that are the gravitational waves. So today we will have a presentation about what has been done, but in particular what can be done in the near future. All of you knows that the INFN community is pretty involved in this gravitational wave study, so we can just we eagerly wait to hear from Massimo what perspective we can have. So I wish to thank again Massimo to be here, and I think that we can leave the room to Massimo to talk about gravitational waves. Thank you very much.
So, thank you for inviting me. And actually, like you said, for me, Catania is home. You know, I've been, I consider myself, you know, part of this community. I've been in relation scientific and with friendship with a lot of people in Catania, and I think that really, to me, is it's an honor to speak in front of the rector of the University of Catania. And okay, so I will start my talk with just remind what are the sources of gravitational waves. So gravitational waves are, you know, are waves like all the other, like electromagnetic waves, and the sources are very different. And I just put here everything which is, conceived right now with some question mark, because some of them are, you know, even, you know, very, I would say, more than exotic. In fact, you know, the region that is nowadays being observed is the one in yellow, and has been observed with only in-ground interferometer. Among the several in the future, I want to mention LISA, which is in the emission in the space, which is supposed to go to very low frequency. In the frequency is important because, like, you know, you can have a mechanical parallel. You know, the higher the frequency, the lower the mass of the sources. So if when you move to very low frequency, you are testing masses that are very, very heavy, and eventually you can even see something coming from relic from the Big Bang. Okay, gravitational waves are interesting per se, but you know, it's also important, and I think that is one of the reasons why INFN tested this, was really interested in this, because it's really related also to fundamental physics, at least what we call fundamental physics. So cosmology, astrophysics, and nuclear physics. I mentioned nuclear physics because in Catania here, there is a school tradition in nuclear physics, and we can collaborate in studying together what's going to happen from gravitational waves. In fact, I mentioned that there are so many different sources, but what we only see are merger. I remember that to see merger are two very heavy objects, like two neutron stars or neutron stars black hole or two black holes that are spiralizing and then eventually they collide together. I remember that gravitational waves are produced by larger masses accelerated with asymmetry. The first momentum of the emission is the quadrupole momentum because monopole, conservation of energy protect the monopole. If you try to write a dipole, then you end up with the conservation of either with the dipole, electric dipole or the magnetic dipole, you end up with the conservation of momentum or conservation of angular momentum. So both of them are not together with the principle of equivalence, that you cannot have anything which is related. So the first, they have to be asymmetric and at least a quadrupole momentum. And in fact, like I said, we only see mergers, and it was the first observation was awarded with the Nobel Prize in 2017. Unfortunately, the Italian collaboration at that time was not ready, and so they missed the Nobel Prize, too bad. And I hope we don't miss the next one. This is where, okay, but so gravitational waves field has been rapidly growing since the discovery. The discovery itself was, like I said, a paramount discovery. But from then, we already observed sort of 200 mergers have been observed, and we are going from the observation mode to the study mode. And in fact, we can do, like I said, a test of gravitational, test of general relativity, limit on the graviton mass, and also the relationship, like I said, with other communities, especially astrophysics and cosmology and negative physics, is increasing. This is how it looks, and the output of the observation of gravitational waves. Each of these square is a merger where you measure the mass of the merger and some of the property of the merger. I have to say that we don't have the sensitivity now to distinguish just from the shape whether it's a neutron star or a gravitational or a black hole. So it's more the masses that that give us the difference. But eventually we end up with being able to separate the kind of mergers. So like I said, it's an old story. It's important to remember that the gravitational waves has been searched since 1916. So it was it's almost 100 years of research. And Einstein itself was very skeptical about the observation of these waves because they are very faint. They don't interact very much with matter, and they are very difficult to see. In fact, the father of this science at the beginning said that itself, Adalberto Giazzotto from Pisa, said that it was just the craziest of the physics enterprise. Anyway, so some nomenclature here. O1, O2, O3, O4, and O is a number that the collaboration use to characterize the data taking. This experiment, like all the experiment in energy physics, have a phase where you build the experiment, then you collect data, then you stop for a while, you improve the experiment, and so on and so forth. And on this you have the cumulative candidate going from the beginning to what have been observed now. I want to mention this because again, it's very important, but also here in Catania, this is very important because in Catania you have the largest telescope for neutrino in the world, and this and the birth of multi-messenger astronomy started with the observation of the event. This nomenclature means gravitational waves and then a number which I don't even remember. I don't want to remember what does it mean, but you know, it's the one that was observed together by LIGO is our counterpart in the United States. So three interferometer observed the event, and what was observed was the coalescence of neutron stars. Neutron stars, when they coalesce, they also emit electromagnetic waves, and this was able, and the first signal arrives as gravitational waves. Then we send an alert. I will return to that, to all the observatory. Everybody point in the sky where we suppose that something happened, and then you can study. And this is supposed to be one of the most promising fields in the next decades. I have to say that this is the only one that we have been observed so far. So I don't know, you know, if you integrate the probability of observing, the efficiency, the acceptance, but you know, people were expecting. I mean, it's something that you know we have to keep an eye on that. I call multi-messenger astronomy because multi-messenger, everybody call this one because you have emission on different radiation, and the difference, like you see, start with the T0 when you have gravitational waves, and then you go on and on and on until 16 days where you have the afterglow, and this is what you expect. I have to say that the kilonova observation is one of the reasons why the astrophysicists actually, community, are pushing us to keep running instead of upgrading our detector, because they really want to, you know, they say that it's more important to observe a new kilonova more than having more larger view of the and wait until next one. And this is a point of tension between us and the astrophysics community. So this is in what I say in my previous slide. You have the time here. The experiment is LIGO, is the name of the interferometer, the two interferometers in the United States. Virgo is one in Kashina here, the European one. Kagra is in Japan and is underground. Virgo and Kagra are 3 kilometer long interferometer, LIGO 4 kilometer. The number that you see is a way of measuring the sensitivity of this interferometer, and this megaparsecs. Megaparsec is the distance at which, with given a certain sensitivity, you are able to see a couple of neutron stars. Why neutron stars? Neutron stars because they have a fixed mass roughly, and they emit at the same, you know, the output is known. Otherwise, if you take black holes, according to the mass, they emit in a different way. So it was decided at some point that you take this as a reference. And you see that starting when LIGO started, they were at 80 megaparsecs. You arrive now, this is 150 megaparsecs. This is what we are expecting in 2028. I have to say that Kagra is not performing like expected. Also Virgo, honestly, has not been, you see, we are at not very better than when we started in 03 for several reasons. And this area here is the area where you don't collect data, but you improve or are supposed to improve the detector. Of course, the better the distance, I mean, goes with the cube of the distance. So, you know, even an increase of a factor of 2 means larger volume of the space that you can observe. So this is the plane of the sensitivity that we expect from Virgo. This is a typical plot that you will see to describe the performances of ground-based interferometer. On this scale, you have the strain as a square divided by the square of S. This is the standard way of representing noise, or in the case of you know, any temporal series of events, and here you have the frequency. The reason why we show this kind of plot is because it's not like in the case of high energy physics where you see a peak of mass, or you just see, basically you have to reduce the noise, lower the noise, you analyze the time sequence of the event, and then you extract the data. And you see that the shape is typically this one with the peak towards low frequencies, and then it's flat roughly in this region around 110 kilo. We have this is 1 kilohertz, 100 hertz, and then goes up again. The scale 10 to the minus 21 is the typical one that you will have for the signal. I will return to that. This is what we expect in Virgo when after an improvement that this is not yet approved, I have to say. INFN, CNRS are discussing whether or not to approve this upgrade. The major upgrade is in the first line, which is recycling cavity and the stable cavity. I will explain later the core of this experiment are Fabry-Perot cavity, which are used to where the laser go back and forth, and according to the optical property of this Fabry-Perot cavity, you can have stable or unstable cavity or marginally stable cavity. This is a terminology that means basically that you are able to filter that higher order mode that are present in the laser cancel because you have enough length to dump the higher mode. And this results in a better way of having the detector, of handling with the interferometer. In the case of Virgo, the cavity were in the regime called marginally stable, and we want to go instead, like in the case of Virgo, with stable cavity, which means longer cavity, but means more money and so on. Like you see from what I said, that there are a lot of competencies that are outside INFN. I am an INFN man because, laser, optics, there are all things that are usually not part of the culture of the INFN. But, so this is a reason why I think that for the third generation, we don't have to make, we really have to increase the community that has to work on third generation, because there are competencies and they are outside INFN. So in the world, how many detectors we have? 2 in the United States. They choose at a very large distance, which is better for pointing to the direction. Then there is Virgo close to Cascina. Geo is the first one that was built, is a 600 meter. It's no longer competitive with the other, but still has been used for developing R&D and new technology. Kagra is in Japan, is underground, is the only one underground, but as I said, is underperforming. This is a very interesting idea that they want to mimic the one that is in United States, in India. And this is, I mean, they expect to have it in maybe 10 years from now. Who knows, but it's really will change the game because you will have really a network of this. Why we need a network, I will return to later, but you have to keep in mind that a single interferometer is not like a telescope that you can point to a place. You can just know that a gravitational wave passed. Then if you have 2, you can start reducing the place where you expect to see the gravitational wave. With 3 detectors, you can really point to, and the more you have, the better. So this is the collaboration. This is the one which is in Cascina. The collaboration, like you see, and I am the director of this interferometer, this laboratory. Like you see, is mainly European, while the other are, but still there are people from Europe that are collaborating with LIGO, especially in Germany and in United Kingdom. The Virgo is mainly Italian and French, I have to say, but there are also NICEF, from Netherlands with a great contribution, and now also Belgium and other are entering into the game. Okay, so I will briefly go on this. The reason why I put this is because the two founders was Adalberto Giazzotto and Alain Brillet. Brillet from CNRS, Adalberto Giazzotto unfortunately passed away. They represent two different competencies. The INFN, mechanics, electronics, and the suspensions, the way to dump the noise coming from the ground. Alain Brillet put all the expertise from the optical and the laser from France, which was, that's why I mentioned that. And also, if I may say something to our friends that are working on Einstein telescope, I'm working, but not very now, because as a director of EGO, I cannot, I'm not supposed to work for Einstein telescope. But it took 30 years from the beginning of to now. So we don't, even if we have green light for Einstein telescope now, don't expect to have everything, something very soon. Okay, this is what EGO is. It's a very small, I can skip it. And again, this is a picture of the tunnel. This is the tunnel where the laser shines. It's actually, what you see here is something just to cover the real tunnel where the vacuum is. The vacuum of EGO is the largest volume of vacuum in Europe. Even CERN is smaller, because even if it's longer, it's very thin. Here you have a meter wide, 3 by 3 kilometers. I want to show this also, and this is also a lesson for people that are designing Einstein telescope. This is at the beginning, and this is now. This second tunnel was not foreseen from the very beginning. Here, this is used for squeezing of the light. Squeezing is a technique that is used to manipulate the phase space of photons in order to reduce the spread of the phase space and reduce the noise related to the photons, and was not foreseen from the very beginning. And they took more space, and when they decided to install this new tunnel, they had room. So I mean, we have to think about, when you build something, not to be too I know that money is important, but sometimes you have ideas that you don't know from the very beginning. So the technology that we have, I mentioned it already from at the beginning. It's something that is really related to the kind of noise that you want to reduce. So vacuum, it's very important to have the largest vacuum that you want, and the technique that you use for the vacuum is not the same that you use for accelerator. You have to remember that vacuum here, you cannot just pump air out, because you don't want to introduce noise, mechanical noise inside. So keeping the vacuum here is not as easy as in the case of the accelerator. The super attenuator is a technique that is basically a pendulum, you can say, that is used to mechanically decouple the mirror that are suspended at the end of the interferometer. And then you have, of course, a lot of work and a lot of expertise goes into the dealing with the laser and the quantum sensing of the laser. In the case of the mirror, there is a very important part of to reduce the thermal noise. It's very important to have a coating and with material that are very specific for this case. And there is only one lab right now, which is in France. It's LMA in Lyon, which can do this kind of work. But anyway, you can see that there is a wide spectrum of technology. I want to return this just to remember, to tell you again where we are. This was last month. We had an exceptional, I mean, I won't call exceptional, because nowadays we have a couple of flooding every couple of months, because of, even if people don't believe in environmental and global change. But we are located very close to this canal, which is used to protect Pisa in the case of the river. If there is an overflow, this canal is open and the water goes out from the river Arno, and we are very close. And in fact, this was the highest level in 2 decades, and we almost risked that I was not here speaking today, but dealing with the problem of overflowing. Okay, so if people know, you can see this, and it's very almost overflown. If people are familiar with the Pisa, that was the river Arno in that time. Okay, anyway, just to tell that sometimes when you pick a place, you have to be careful where you put your apparatus. Anyway, so this is a picture where I'm showing what I mentioned before, how you can localize the source of gravitational wave. Those are Hanford and Livingston are the places where they are located, the one in the United States. Virgo is, now what it is. And you can see that from these images that the resolution of Virgo is worse than Livingston and Hanford, clearly. They can better see the shape. And actually, Livingston is better than Hanford, even though they are very similar. Understanding why the sensitivity of this instrument is, or like we say, the noise budget of the interferometer is very difficult. But you can see that even with a resolution which is not as good, we go from this to this to this. And so with 3 interferometer, you can pin down to a very small region, even if the resolution is not as good as the other one. This is in the case of several years ago. And the localization is 100 degrees square, which is not bad if you know what is the resolution of the moon, for example. Now we are much better. This was the first event seen by the 3 events. Now that's what we see. We go from here to here. So we are able to really localize in the space with a very good resolution the area where the interferometer comes. Again, an interferometer just is enough for you to know that past 1 gravitational waves. With 2, you can have this shape like banana shape, and then with the 3rd one, you pin down to the. In fact, you can have a sort of an antenna effect because gravitational waves have a polarization. And so even with a single one, you can have a sort of directionality, but it's much worse than having 3 different interferometers. So what's the effect of gravitational waves? I don't know if this will animate, but basically if you have something like that where you have these 2 merger that spiralize, they modify the space-time, and when they reach for example, a circle of you have a deformation that is basically this squeeze, and this goes like this. That's the effect. And in fact, in the interferometer, what you have is one of the length of the arm shrink and the other one becomes longer, but by a factor which is 10 to the minus 3 the size of a proton, so nothing. But that's the effect that. And if you have another polarization, the other polarization is 45 degrees with respect to this. The gravitational waves has 2 different polarization, this one and another one rotated by 45 degrees, which again points to the fact that graviton has a spin 2 and not spin 1, and so the polarization is 45 degrees. So how do you see the passage of gravitational waves? The idea is to reuse a very old idea, which is the Michelson interferometer, which I imagine from school. I mean, has been studied, and this is a very good experiment, and as all the ideas that was used, and also they know that they had to float the interferometer to reduce the noise. Maybe you know that in our case, what has been done is that just you have the idea is the same. You have a laser, you split, and then you recombine, and then in the end you have these 2 mirrors, and then they recombine, and you end up with a photodiode that measures the intensity of the laser. So you just, if you want to define in a very general, this is just a transductor of intensity of laser, different of length into intensity of the laser. For people that are familiar with the original interferometer, original Michelson interferometer, they were not able to measure the intensity. They made a trick in order to see the movement of the fringe of interference, but this was a trick because they were not able, we didn't have the photodiode at the time. And they were very clever in doing that, and they modified a little bit with respect to this scheme. In our case, you just have the intensity here, and of course, if the length are exactly the same, you have a maximum or a minimum, and then you can say that the wave is passed or not. Of course, the things are much more complex than this, because you have other cavities that are used to clean up the laser that enter into the interferometer. But I put here what are the characteristics of the laser. If you put the intensity or the typical intensity of the gravitational waves, gravitational waves came as a solution of the Einstein equation in the case of they modified the space-time in the case of small intensity. If you expand, you have a wave equation for the space-time, and the parameter, which is called h, is the one that gives you the ratio between the difference of length and the length. And this number is of the order of 10 to the minus 21, roughly. If you put this number and you try to see how long they should be, you end up with a number which is huge, and you cannot measure. In fact, the reason why we use this trick is that first of all, the Fabry-Perot is a way to have this longer. The longer, they stay more than. And also the fact that we use the interferometer and we measure the intensity, you can see that in the end, if you measure the intensity, you are not limited by the space resolution, of course, but you are limited by the counting of the photon. So the more you add in the power of photon, then you have a better resolution. If you put everything this together, you end up that you need something of the arms that are longer of the order of kilometer, masses of the order of 40 kilograms, and you have also we have to suspend this mirror. This is an example of a mirror that they have to be suspended from the ground because you want to, in principle, to measure to the effect of gravitational waves is seen when those are in free falling. You have this. You have to imagine that this mirror are like free falling. How do you realize free falling? You add a filter, a electromechanical filter that cut the frequency, so they are free falling according to the frequency. I return to what I mentioned at the beginning. So from this slide, you can understand, what you have to know to make working an interferometer. So the importance is to reduce the noise. Noise is the devil in our case. You have to fight to understand the noise and lower the noise. Some of the noise you can predict from a first principle, and at high frequency you are limited by the shot noise. That's what I mentioned. The number of counting of photons. In the mid frequency, you are limited by shot noise and radiation pressure. In low frequency, radiation pressure is limiting you. You have just the pressure of the laser on the mirror is enough to create a noise. And here already you see that there is you have to balance, because shot noise requires higher power. Radiation pressure, better to have a lower power. So it depends what you want to do. The reason why we have to do this is because with the single interferometer we want to measure all the frequencies. If you know the history of gravitational waves, at the beginning there were different detectors. The detectors were called resonant bar that were supposed to mechanically resonate when the waves heated. But those were only on a single frequency. The reason why they badly failed, is that they were tuned to a single frequency, and they were not able, and even the frequency was not exactly what they were expecting. The interferometer is a broadband. So, you know, you go from very low frequency to high frequency. And this is the reason why with the same interferometer, you have to fight with different noise. Then another one which is very important at low frequency is the thermal noise. You go down, and the limiting eventually is the Newtonian. The Newtonian noise is we call with the Newtonian noise every noise that comes from the interaction of masses moving around the mirror. Even larger masses moving, they can induce gravitational attraction, and this can create noise. But I'm really want to say that this is I call control noise, but this means instrumental noise, because before reaching the limit, you have to have all your apparatus in control, and you don't have, and this is very difficult to monitor, because all the other, they can predict it from first principle, and you can reproduce in the dependency from the frequency. Control noise is something that don't know. And actually, this is the case now. We have a noise around 200 kilohertz, that is 200 hertz, which is limiting a lot, and we don't know. In fact, they call mystery noise, which I don't think is a very good name, because if you still have a mystery noise, what means that you don't understand your detector, but that's the way it is. I am returning to this, and because different region, like I said, corresponds to different sources. Low noise, low frequency, like I said, means high masses and early warning. Why I say early warning? I can return, maybe I can just describe it. Have you seen that the signal as a function of time of gravitational waves starts, oh, maybe it's, you know, I can it's not, I can read, oops, sorry. Where is it? Oops, where is, is going back or no? How can I go back? Oh, sorry. This is, so we take a little break here. I can take this shape here. You see that it starts at a low frequency, then you have the merging, high frequency, and then you have the ring down. So the more sensitive you are at low frequencies, the earlier you see the gravitational waves. And that's why you want to go to low frequency, not only to see larger masses, but also to see the signal earlier and to follow the signal for longer. This is very important also for the multi-messenger. So the very important part of the spectrum is low frequency. Again, not only because you want to see different masses, but because you are able to see and follow the phenomenon for several days. Okay, let me return to where I was. I spoiled the most of my talk, which is good. Okay. No, sorry, I'm okay. Where I was, oops. Okay. Sorry, oops. Okay. So again, you know, this is the typical curve. So if you want to reduce the central part, what you have to do is to have a better mirror technology. You know, if you want to reduce the noise at high frequency, you have to work on the squeezing. Squeezing, like I said, is a technique used to manipulate the phase space of photon. You can squeeze if you take the phase space of photons and you take a amplitude versus phase of two photons, you sum, you end up from the principle of Heisenberg that they occupy a space. If you can rotate this either in the frequency domain, or either in the phase domain or in the amplitude domain, and you can reduce the width of the observed photons. And this is done by the squeezing. You can have a frequency-dependent squeezing that is also able to reduce at low frequency the noise. And if you want to go to lower freezing, then you have to work on the suspension, thermics, and to environmental noise. This is important for the choice of the site. Okay. Here is what I was mentioning. I don't even remember that I had the picture. So this is the typical phase space of photons in a laser. If you rotate, you can end up with the smaller projection and to reduce the noise associated with the fluctuation in the photon. This is a technique that has been imported from the photon science into these fields. Okay, I can skip this because I already said most of these things. Okay, I already discussed this slide. So this is the shape that we have. You can see that, before to arrive to see this one, you need to study. There is also a difference whether you know the shape of the signal or you don't know. If you know the signal, of course, you can improve signal to noise, which is like the case of the spiral. In the case of the spiral, you are able to predict the curve very, very well. Okay. Future upgrades. So future upgrades are, like I almost said what you can do with the current generation. You can work with the current, basically with the current generation, you are fixing the length of the interferometer. The only thing you can do is to improve the technique that you have, but you are still limited by the fact that you have a fixed length. So that's why people are thinking of having a new interferometer. But before going to that, I mentioned and that we have which is very important for the case of the multi-messenger astronomy. We have what we call a rapid response team, which means that for every signal that we have, we analyze very fast according to some, fixed shapes that we know. And after that, we send an alert to all the other lab in the world. I always say this one because it's important. In a moment of, we are living in a world now that is raising walls between countries, and which I don't like it. But this is a proof that if you want to really understand what's going on, you really have to go global. So we start with the signal, we send the alert to everybody. Everybody point their detector, and this is the group of people that are doing this job. This is the first data that I can show you actually from the new run. And I show this one because it was seen that a compact object with a mass around 2.5 solar mass, and apparently this is still studied, but why is this very important? Is because this can mean that there are more black holes and neutron stars at lower mass than we expect. So, this is promising for the multi-messenger implication, because like I said, we have seen one. But in the new run, we have seen that there is a possibility that we have signal with different, with lower mass. We haven't seen the multi-messenger event, but this changed the shape and the probability to observe more neutron stars at black hole. I'm rushing this because I want to speak about the next generation, which is, so the next generation is called third generation, and is basically divided into different, this is the future in the United States. This is what we have in Europe, sorry. In Europe, it's called the Einstein telescope. They are called Cosmic Explorer. The Cosmic Explorer is more or less the one that we have, but just with the longer arms. I mentioned already that the length of the interferometer is a measurement, is a factor limiting the sensitivity. So they go to longer, even to 40 kilometers. They are proposing two different interferometers, one of 40 kilometers and another one of 20. The reason why they have two different is just for money, because this one costs less, but of course the longest the better. And they have they are separating the two configuration, high frequency and low frequency, because I mentioned before that you sometimes, if you want to optimize for a high frequency, you lose a low frequency. Remember shot noise versus the radiation pressure. In the case of Einstein telescope, there is a more complex situation. First of all, we want to go underground. Underground means reducing the noise coming from the Earth. I mean, or the noise which is related to the seismic noise, but also human noise. In the case of the United States, it's much easier also to have this very long space outside. If you remember the one that I showed in Kashina, we made 3 kilometers for no other reason, because on one side we had the river, on the other side we had the mountain. So I mean, it's there is often the people ask me why 3 kilometers, and they think that was a very profound reason. The reason is not, I mean, very profound, but just because we don't have enough time close by. So anyway, we want to go underground, and here there is a lot of discussion where to put this facility, and it's very hot, the discussion, because there are at least 3 sites: Sardinia, Holland, and Sassari. And also there is a discussion about, and I will do it later, I will comment on that, whether to move from originally it was thought to be a triangle, because a triangle is like, having 2 L close, and so it's enough as a sort of directionality. You remember that I mentioned that you need at least 2 or 3. When Einstein telescope was proposed at the very beginning, they were expected to have just one, and so with just one you can have with a triangle you are able to point, which is the same solution for people that are familiar with the LIDA, the one in space. It's also a triangle going around because with the triangle you can, you don't have a very good resolution, but if you move this triangle, you are able in the end to point. Anyway, so United States, same technology, just make it bigger, longer, and separate high frequency from low frequency. Einstein telescope, make it longer and go down underground. I mentioned 3 different locations. One is the two that are from now have been mostly where most study has been done is Sardinia, and in Netherlands, actually close to Maastricht, is at the border of Belgium, Netherlands, and Germany. And then, but now there is another one. Germany proposed another in Sassari, another sites, which looks very promising too. I'm very, the one in Sardinia, I can, like direct ego is a lab which is France, Italian, and Netherlands. So by definition, I cannot take any role in choosing which one of the 3, because they are, if the director of LIGO is a supporter of this one, then they won't be very happy to pay my salary. But when I started, before going, I was the rector of the University of Sassari, and honestly, I was instrumental in picking that spot because it's very, very good for several reasons. But I think that sometimes if you have a person in the place that really believe and push the political environment, this can make the difference. Anyway, so this is the situation. They are fighting to decide where to put it. I don't want to enter into this, but I want to mention this because after the story of Einstein telescope, it started like a triangle, but now, especially in Italy, we propose to have 2L and one in one of the 2 places, to have like we did they did in United States. Unfortunately, the community is not completely in favor of this. Especially in the Netherlands, there is a strong support still of this design, but this is delaying somehow the decision, and so on and so forth. Anyway, this just I'm saying again what what I mentioned briefly. Now you know why. For high frequency, you can go to high power, room temperature. You don't need to go cryogenic because you are not limited by thermal noise. If you go to design the low frequency, you can reduce the power, go cryogenic. So to having two separate cost more, but you have two different detector. The Einstein telescope collaboration is mainly, like you say, European. This is a problem because the same people that are working on the Einstein telescope are the same one that are working on Virgo, so they have to split between the two. But okay, anyway, I think I'm running out of time. Probably I can just, flash the technology that you need is just you have to take the technology are basically the same, but you have to push them more. The most important part, but I don't think it's going to happen for the first generation, is to go cryogenic. The only cryogenic that you have right now is Kagra, which is underground and cryogenic, but like I said, it's not completely working. Why? I think that cryogenics needs a lot of development. So new coating, thermal compensation, I mean, all the things that I mentioned, you have to push it to go to Einstein telescope. This is the candidate that is in Enattos that I mentioned before. And why is a low, that region is a low seismic noise, and there is the less populated part of Europe. So it's a special, it's very good from the point of view of the ground, but also there is no noise around. Those are studies that have been made. I can skip this. And the crucial point is that with the several borehole, the measurement has been done, and it's clear that this part is it's very good to reduce the noise, which is important at low frequency. The colleague in Netherlands, they are putting this, like I said, in this triangle. They are in a much more crowded environment. They say that they are able to reduce the noise around. We have to believe them. But, you see that you are close to this TGV. There are, but anyway, this is, I'm not in the game of choosing the sites, but, I'm just reporting to you that this is the situation right now. And they also mentioned the fact that due to the nature of the ground, even if they have a lot of noise, the ground itself, from the geology, lower the noise. Who knows? Newtonian noise, again, is the limiting factor, like I said, and okay, this has been done. So summary. The future gravitational wave is a compelling scientific case. So going to lower frequency, like I said, has several reasons. There is no point that going to lower frequency will improve the physics. They rely on solid technique, I have to say, but the R&D is needed in several areas to reach 10 to the minus 25 to square root of Hertz over a wide range of frequency. This is something that in the case of INFN, I think it's important to discuss. Going from Virgo to Einstein telescopes is at least 4 orders of magnitude of sensitivity. So I say to Alessia, because she will be part of the decision to whether or not to finance this experiment. It's important. It's certainly doable, but it's not like from 400 of magnitude in the noise at low frequency. It's not something that you do without a strong R&D program, which I don't see now. The low frequency noise is still not tamed. In Virgo right now, we are 2 orders of magnitude worse than was foreseen. And the reason is not intrinsic noise, but it's instrumental noise. So, if we don't understand exactly what are the sources of noise, we don't end. And also, like I said, Virgo and LIGO are fundamentally, people, if they really want to go to 3rd generation, they have to work on Virgo and LIGO to understand the physics and move to the next generation. So we still have room for working to improve the detector. So my final slide is that I think that gravitational waves are a key point to understand the cosmology, but they have to be inserted in a broader picture, which include other study like microwave background, which is another CMB, is another important area. If you want to really make a study of what the standard model of cosmology, you really have to work in a global world. And this, to me, it's very important that we have to work with the particle astrophysics and cosmology. Honestly, this is something that which I always say, that future gravitational infrastructure are a challenge and opportunity to involve people from different fields. You cannot do this with the current community. You have to involve more people inside high energy physics, but also from people that are expert in laser, material science. It's very crucial. It's very crucial. So, if you want really to go to the third generation, we have to really take all these opportunities together. And the final lessons that I think we have to learn from now, that when we started gravitational waves research, Europe and United States were competing. The first one get the prize, and we lost. Okay, too bad. But the future is that we have to start thinking from the very beginning like a global enterprise. If you think of the Earth, like you would need at least three. On the physics dictate that you need three spaced in the largest two, maybe in the northern hemisphere, one the south. Okay, so you really have to think of this like a global enterprise, because it's no longer who's going to be the first one to observe, but we have to build a network of interferometers, and we have to work closely with our colleague in United States, Japan, and which is getting more and more difficult, I have to say. Thank you.
Thanks a lot, Massimo. Now,